The transformation from solid wood logs into ultra-smooth A4 paper is one of the most impressive examples of industrial engineering precision in the modern world. What begins as a dense, fibrous, moisture-rich tree trunk in a plantation eventually becomes a perfectly flat, bright white, lightweight sheet that slides effortlessly through printers and copiers. This journey is not simple. It is a carefully synchronized sequence of mechanical force, chemical reactions, chemical rheology, filtration, pressure control, moisture regulation, and surface engineering, all operating continuously inside a highly automated production environment. The process begins with harvested logs arriving at the mill in uniform lengths. These logs are not random pieces of timber, they are selected and prepared for consistency. Their diameter, density, and moisture content influence how efficiently they can be converted into pulp. Once unloaded, they are fed into enormous rotating drum debarkers. Inside these massive steel cylinders, the logs tumble and collide against each other. Friction loosens and strips away the bark without damaging the valuable inner wood. This step is crucial because bark contains dirt, sand, and darker organic compounds that would reduce paper brightness and quality. Removing it ensures a clean starting point for fiber extraction. After debarking, the logs move toward high-capacity chipping machines. These industrial chippers operate with razor-sharp rotating blades capable of slicing entire logs into small, uniform wood chips in seconds. Precision here matters more than it may seem. If chips are too thick, they won't cook evenly during pulping. If too thin, they may overcook and weaken the fiber structure. Screening systems sort the chips, recycling oversized pieces back through the chipper while directing correctly sized chips forward. Uniformity at this stage determines consistency later in the process. The wood chips are then conveyed into towering digesters, some of the most imposing structures inside the factory. These vertical steel vessels operate under carefully controlled high temperature and pressure. Inside, the chips are cooked in a chemical solution designed to dissolve lignin, the natural polymer that binds wood fibers together. Lignin is strong and rigid, it gives trees their structural stability. However, for papermaking, it must be separated from cellulose fibers. The chemical cooking process breaks lignin down into soluble compounds, freeing the cellulose fibers without excessively damaging them. This stage is transformative. Inside the digester, hard wooden chips soften and break apart into a fibrous mass. The process requires precise timing, temperature control, and chemical balance. Too little cooking leaves fibers stiff and dark. Too much cooking weakens them and reduces paper strength. Automated control systems constantly monitor pressure levels, chemical concentration, and cooking duration to maintain the perfect balance. Once cooking is complete, the pulp, now a thick, brown mixture of cellulose fibers suspended in liquid, exits the digester and moves to the washing stage. Here, multiple washing systems rinse away dissolved lignin and spent chemicals. This cleaning phase improves fiber purity and prepares the pulp for brightness enhancement. The washing process also separates out dark liquid byproducts, which are later processed to recover energy and reusable chemicals, improving overall efficiency. Although washed, the pulp still carries a natural brown tone due to residual lignin. To create bright white office paper, bleaching is required. Modern bleaching sequences rely on environmentally controlled methods that reduce harmful emissions while achieving high brightness. In multiple stages, safe oxidizing agents remove remaining color bodies without degrading fiber strength. Each stage increases whiteness incrementally, while laboratory sensors measure brightness levels in real time to ensure uniform results. After bleaching, the pulp transforms visually and physically. It becomes a soft, nearly white mass composed of millions of microscopic cellulose fibers. At this stage, the pulp is stored in large tanks where consistency is adjusted. Water is added or removed to achieve the precise fiber concentration needed for sheet formation. Surprisingly, when it is ready to enter the paper machine, the mixture contains about 99% water and only 1% fiber. That dilution is essential for even fiber distribution. The diluted pulp slurry is pumped into the forming section of the paper machine, the true heart of the factory. This machine can extend longer than a football field and operates at astonishing speeds. The slurry flows out evenly across a rapidly moving wire mesh conveyor. Gravity and vacuum suction systems beneath the mesh begin removing water instantly. As water drains away, fibers settle and interlock naturally, forming a thin, wet mat. At this early stage, the sheet is extremely delicate. It has shape but very little strength. The magic lies in how cellulose fibers bond together. Each fiber has microscopic fibrils that intertwine and form hydrogen bonds as water leaves the structure. These bonds are the foundation of paper strength. The more evenly fibers are distributed, the stronger and smoother the final sheet will be. From the forming section, the fragile sheet moves into the pressing section. Here, it passes between massive rotating press rolls covered with absorbent materials. These rollers apply immense pressure, squeezing out additional water while bringing fibers closer together. Pressing increases fiber bonding and improves sheet density. The moisture content drops significantly, but the sheet still contains enough water to require further drying. Next comes the drying section, one of the most visually dramatic stages in the factory. The paper travels over dozens of large steam, heated cylinders arranged in sequence. Each cylinder gradually evaporates remaining moisture. The sheet weaves back and forth over these heated surfaces at high speed, losing water steadily while gaining strength and dimensional stability. Temperature control is critical here. Uneven heating could cause warping or variation in thickness. As drying progresses, the sheet becomes fully formed paper. However, for high-quality A4 office paper, surface refinement is essential. After drying, the sheet may pass through a sizing station where a thin coating is applied. This treatment improves ink absorption, prevents feathering during printing, and enhances smoothness. Without proper sizing, printed text could blur or bleed. Following sizing, the sheet enters the calendaring section. Heavy polished rollers compress and smooth the surface further, improving brightness, uniformity, and tactile feel. Calendaring determines the finish, whether matte, silk, or high smoothness. The pressure applied must be balanced carefully. Too much pressure can make paper overly dense and reduce opacity. Too little leaves surface texture inconsistent. At this point, the paper is wound into enormous parent rolls. These reels can weigh several tons and measure several meters in width. The continuous sheet that began as watery pulp now exists as a strong, flexible, perfectly uniform roll of paper. Automated systems monitor roll tension to prevent wrinkles or tears. The conversion stage follows. Parent rolls are transferred to high-speed slitters that cut them into narrower rolls suitable for A4 dimensions. These rolls then feed into sheeting machines equipped with precision rotary knives and guillotine cutters. The machines slice the continuous web into exact 210 by 297 mm sheets at remarkable speed. Accuracy here is measured in fractions of a millimeter. Stacks of freshly cut sheets are aligned automatically to ensure sharp edges. Airjets and vibration systems keep sheets perfectly square. Counting systems separate them into standard 500-sheet reams. Each stack is pressed lightly to remove trapped air and ensure flatness. Quality control continues throughout. Optical scanners inspect sheet thickness, formation uniformity, brightness, and surface defects. Any deviation triggers adjustments upstream. Laboratory tests measure tensile strength, stiffness, opacity, and moisture content. Office-grade A4 paper must run smoothly through high-speed printers without jamming, curling, or smudging. Achieving that reliability requires microscopic precision at every stage. Finally, the reams are wrapped in moisture-resistant packaging. Automated machines fold and seal protective wrappers tightly around each stack. The packaging not only protects against humidity, but also maintains sheet alignment during transport. Multiple reams are boxed, labeled, palletized, and prepared for distribution. The most extraordinary aspect of this transformation is the scale combined with precision. What appears to be a simple sheet of paper is the result of complex fiber chemistry, thermodynamics, and mechanical engineering. Every fiber has traveled through intense heat, pressure, and controlled bonding. Every sheet represents the coordination of hundreds of synchronized systems operating in harmony. From the outside, A4 paper may seem ordinary, but inside the factory, its creation is a continuous, high-speed ballet of machines, chemistry, and control systems. In just a few hours, a solid wood log becomes thousands of perfectly smooth sheets ready for offices around the world. The journey from forest fiber to flawless surface reveals the remarkable sophistication hidden behind one of the most common products in everyday life. Sustainability and energy efficiency have become cornerstones of modern industrial manufacturing, and nowhere is this more evident than in the production of A4 paper at large-scale factories like PaperOne. While the intricate transformation from wood logs to smooth paper sheets is impressive, the underlying processes that ensure environmental responsibility are equally remarkable. The factory operates on a holistic approach that integrates sustainable forestry, resource recycling, energy recovery, water treatment, and waste minimization, demonstrating that high-end production and ecological stewardship can coexist. The first element of sustainability begins far upstream in the supply chain: the forests themselves. PaperOne sources its wood from carefully managed plantations, predominantly fast-growing species like eucalyptus and acacia. These plantations are not just vast areas of trees, they are meticulously planned ecosystems. Trees are planted in rotational cycles, meaning that for every tree harvested, new saplings are planted immediately to maintain forest cover. This practice prevents deforestation, preserves soil quality, and maintains biodiversity by incorporating buffer zones, wildlife corridors, and mixed species plantings in certain areas. Plantation managers track soil nutrients, growth rates, and water use to optimize tree health without excessive fertilizer or pesticide application. The result is a renewable, high-quality timber source that reduces pressure on natural forests and contributes to long-term ecological balance. After harvesting, the bark removed during the debarking stage, along with other wood byproducts, is far from wasted. Instead of being discarded, these materials are used as biomass fuel in recovery boilers. These boilers generate the majority of the steam and electricity required to run the paper mill. Burning bark and black liquor, the dark liquid byproduct of the pulping process, produces thermal energy that powers the digesters, drying cylinders, and other high-consumption machinery. This internal energy generation dramatically reduces dependence on fossil fuels and lowers the factory's carbon footprint. In effect, what could have been waste becomes a primary energy source, showcasing a closed-loop approach that integrates energy recovery directly into production operations. Water use, another critical resource in papermaking, is managed with equal care. During pulping, washing, and sheet formation, large quantities of water are necessary to transport fibers and remove residual chemicals. Rather than discharging this water as wastewater, the factory employs sophisticated treatment and recycling systems. Wastewater is collected and processed in treatment plants that remove suspended solids, residual chemicals, and color compounds. After purification, the water is recycled back into the pulping and forming processes, reducing overall water consumption dramatically. The efficiency of water reuse in modern mills can reach up to 90%, meaning very little fresh water is needed compared to the volume processed. This cycle not only conserves a vital natural resource, but also minimizes the environmental impact of chemical discharge on surrounding ecosystems. Chemical use itself is carefully controlled to reduce ecological harm. In the bleaching process, modern factories adopt elemental chlorine-free or totally chlorine-free techniques, which prevent the formation of harmful chlorinated compounds in effluent. Advanced monitoring ensures precise chemical dosing, balancing the need for brightness with fiber preservation and environmental safety. Even when chemicals are used in digesters to break down lignin, recovery systems capture and recycle them wherever possible, reducing both raw material consumption and wastewater contamination. This attention to chemical stewardship is critical in large-scale papermaking, where uncontrolled chemical use could have significant downstream environmental consequences. Energy efficiency extends beyond biomass use. The layout of the factory and its machines are optimized to minimize energy loss. Steam generated in recovery boilers circulates through interconnected digesters, drying cylinders, and heating coils, creating a cascade of thermal energy. Motors and pumps are often high-efficiency models, and conveyor systems are designed to reduce friction and mechanical strain. Automation plays a significant role. Sensors adjust machine speed, temperature, and pressure in real time, ensuring that energy is applied precisely where it is needed. Continuous monitoring of energy consumption helps managers identify areas for improvement, making the entire facility a living model of industrial energy optimization. Even the handling and packaging stages incorporate sustainability principles. Modern mills use robotic systems for stacking, wrapping, and palletizing paper reams. Robots operate with high precision, reducing material waste caused by misalignment or human error. Packaging materials themselves are chosen for durability and recyclability, often incorporating moisture-resistant, biodegradable films that protect paper while remaining environmentally friendly. Palletization and shipping logistics are optimized to maximize space in transport vehicles, further reducing fuel consumption and carbon emissions associated with distribution. The factory's commitment to sustainability is also reflected in its waste management policies. Solid waste, including rejected fibers, trimmings, and off-spec products, is segregated and often repurposed. Some fiber waste is reintroduced into the pulping process, while other residues may be composted or used in energy generation. By viewing waste as a resource rather than a liability, the factory minimizes landfill use and contributes to a circular industrial economy. This holistic approach underscores the philosophy that every material, whether product, byproduct, or discarded fiber, can be reintegrated into the system. Sustainability in paper manufacturing is also about scale and global impact. Producing millions of sheets daily requires careful consideration of carbon emissions, resource use, and environmental footprint. By combining renewable energy sources, closed-loop water systems, responsible chemical management, and sustainable forestry, factories like PaperOne demonstrate that industrial production does not have to come at the expense of the environment. Each sheet of A4 paper carries with it a story of energy optimization, resource stewardship, and ecological responsibility. Another critical aspect is employee training and operational culture. Sustainability initiatives are only effective when staff understand their role in maintaining efficiency and minimizing waste. Operators are trained to monitor energy consumption, handle chemicals safely, and respond quickly to any system variations that could lead to inefficiency or environmental harm. Management emphasizes continuous improvement, encouraging innovation in reducing energy use, enhancing recycling, and improving resource efficiency. This culture ensures that sustainability is not a static policy but an ongoing, evolving practice embedded in every stage of production. The integration of sustainability and energy efficiency also contributes to economic resilience. By generating a significant portion of energy internally and recycling water and chemicals, the factory reduces operational costs and dependency on external utilities. This model demonstrates that environmental responsibility can align with financial efficiency, creating a system where ecological care and industrial productivity reinforce each other. The ability to produce high-quality paper while maintaining low environmental impact gives factories a competitive advantage in markets increasingly focused on green products. Finally, these sustainability efforts have a broader societal impact. They support global goals for responsible resource use, reduce pollution, and contribute to carbon reduction efforts. By sourcing raw materials responsibly, recycling energy and water, and minimizing chemical impact, modern paper factories set a benchmark for other industries. They also provide education and transparency for consumers, showing that everyday products like A4 paper can be produced at massive scale without compromising environmental integrity. In conclusion, the PaperOne factory exemplifies how large-scale industrial operations can integrate sustainability and energy efficiency at every level. From responsible forestry practices to biomass energy recovery, from closed-loop water treatment to precise chemical control, and from automated material handling to optimized logistics, every element is designed to conserve resources and reduce environmental impact. The result is a facility capable of producing millions of sheets of premium A4 per daily, while minimizing its ecological footprint, proving that industrial efficiency and environmental stewardship are not mutually exclusive, but mutually reinforcing principles in modern manufacturing.